All right, everyone, let's have a quick look at what you need to know with regards to Newton's third law, the normal force, and force due to friction. They're all kind of connected together. That'll help you get through some of the remaining questions we have with regards to dynamics. You should really start off with Newton's third law. So that's what we're going to take down for notes. And I think a lot of you actually know this. You may not know that you know it, but we've all kind of heard that expression before. That for every action, there's an equal and opposite reaction, which if you want to throw in the words force, then it really kind of draws into what we've been talking about so far about how force influences motion. So we'll take that down, that for every action. And I'll say for every action force, just to incorporate that, there is an equal and opposite reaction force. And a real common example is like what you're experiencing right now. You're probably just sitting there somewhere at your kitchen table or at your bedroom or what have you, and the force due to gravity is pulling you down, but it's pressing you against the floor, and the floor obviously has to push back up, because if it didn't, the only force you would have would be unbalanced, and you'd be accelerating towards the ground, which you're not currently doing. So what we want to see is that for us, this manifests as a normal force. And the reason they call it normal is just based on the word orthonormal, which is a fancy word of saying perpendicular. So you can think of it as the perpendicular force. So I'll put that other segment in. Get this camera adjusted for you so you can see a bit better. There we go, let's do that. And we're going to give it the letters F sub N, and I use a capital N. I encourage you to use capital N because that's what's in your textbook, and if you use a small n, it's easy to confuse with net force, and it's a small detail, but let's just do the small things to make a big difference for us. So net force F sub N, and we'll see that that's really the perpendicular force of a surface pushing back against an object. So that could actually, in this case right here, be this pad of paper that I have sitting on top of my kitchen table. And the kitchen table is pushing back with whatever force that that gravity is pulling it down with. Now, what I don't want you to get in your minds right now is that the normal force and force due to gravity are always equal. They often are, but in situations where they're not, is me doing something like this. Like if I'm pressing down on this pad of paper, if I was to personify the table, it would think that the paper was heavier than it actually is. Or if I was to lift up on it without actually removing it from the table, it would appear lighter. You can do this yourself when you stand on a bathroom scale. Even though it's measuring in pounds, it's still a measure of force. That if you get your weight, which is your force due to gravity, and then you place your hands on a vanity nearby and kind of lift up a bit, all of a sudden magically you weigh less. And if you put your hands underneath the vanity top and pull up on it, which pushes you down, then your weight seems to be more. So the notion that the normal force always being equal to the force due to gravity isn't necessarily true. It's just situation dependent. But where this connects to our final piece, which is the force due to friction, is that, friction, as we've discussed before, is merely this resistive force, that if you have any two surfaces in contact and there's motion between them, or an attempt to have motion between them, then you're going to run into resistance, which is what the force due to friction is. So I'm going to tag that on here. So it's connected to normal force. We're going to have this equation that force due to friction, F sub F, is going to be mu. Now that's that same Greek letter you saw when we talk about the prefix of micro. And in this case here, it's just a representation of a coefficient. And coefficients, for you math nerds out there, remember this is a number that sits in front of a variable, but it actually has no units. So our formula that we have to calculate the force due to friction is the coefficient of friction multiplied by the normal force. So mu coefficient of friction, and it is unitless. It's not like a force that has a value of newtons. FF, force due to friction, and Fn, normal force. And as the case with all forces in our unit, the measure is newtons. And you see we're running this space there. I'm going to move this a bit. There we go. So that's just kind of a brief intro to what this stuff actually means. Now how we determine what coefficient of friction is, there's ways of calculating it. I mean, you could just take this equation here and rearrange it so that mu is FF divided by Fn, which really describes that it is a description of how big the force due to friction is compared to the normal force. For now, I'm going to use a really unscientific way of explaining it, which is mu, the coefficient of friction, is the relative stickiness. And that's a ridiculous term to use, but it's what kind of makes sense. Is the relative, I'll put in quotes, stickiness. I didn't even spell it right. That's a terrible word. Your English teachers are going to cringe. Between two surfaces. The value is usually between 0 and 1. It doesn't have negative values. It's not going to go over 1. We're going to assume that all situations where two surfaces are in contact, that one is not breaking through the other surface. So if you're thinking of things like, I wear a pair of cleats on a soccer pitch or in a field or what have you, your cleats do actually break through the surface. But I want you to imagine a scenario where it's more along the lines of wearing cleats on a concrete surface. You're never going to see in our physics problems situations where the two surfaces break. They're going to be, for all intents and purposes, completely solid. That's really about it. We will delve into more detail when I see you next. We're going to talk about how there's two different kinds of coefficient of friction. One has to do with two objects that are not moving relative to each other. So it's like pushing on a really heavy safe that's sitting on the ground, and you're not applying enough force and it's not budging. I mean, friction's resisting that. It's preventing you from moving it. That's a form of static friction. Static meaning not moving. Once you get it moving, though, the friction actually declines. It goes down because the coefficient of friction for things that are moving, the kinetic coefficient of friction, is always less. So in other words, it actually takes more force to get an object to start moving than it does for it to continue moving. And we're going to see this manifest in our next lab that we're going to do later this week or early next week. So the calculations that are going to arise from this still come down to the concept that we're going to see an object. So our free body diagrams that are just the pictures that show force acting object are going to start to look like this. Whatever the object is, it's going to have a mass, remember in kilograms. There's always a force due to gravity acting down. That's a guarantee. You can always calculate this as mass in kilograms multiplied by the acceleration due to gravity of 9.81 meters per second squared. Make it negative because it's pointing down. Normal force is going to be up, in this case perpendicular to this surface that I'm drawing. An applied force, which is a push or a pull trying to achieve motion, and a force due to friction, which is always in the opposite direction of motion or attempted motion. Now, the normal force can see situations where it's not pointing up and down like this, like it's pointing up from the surface. If the surface itself is vertical, like as an example, like a wall, and you have a textbook placed against it, and you're using your hand. Here's a lovely drawing. There's a hand, an arm, and they're pushing this way, holding the textbook up against the wall. Then the normal force in this situation, Fn, is going to be horizontal. But notice that's still going to be perpendicular to the surface. That's a consistency of the normal force. Whatever you draw for the surface, the normal force is perpendicular to that. So the problems you're going to now involve, you're going to be dealing with are situations where you know the applied force, you're given the the coefficient of friction, you're given the mass, and you're asked to find its acceleration. So, if you have the mass, you can find the force due to gravity. If these two are balanced out, you have the normal force. You multiply it by coefficient of friction to find the force due to friction. So it's a comparison between these two, and you're back to where you were with those questions, with those boxes, where if you had like 10 newtons of force due to friction and 12 newtons of applied force, you have 2 newtons overall, and you divide that by the mass, and you have your acceleration calculated. So that's really about it. Hope that helps. Send me any messages, any questions you have through Teams, and I'll try to get an answer to you when I see them tomorrow.